If you're doing VCE methods, you need to be master of inverse functions before your first SAC. In the first question, we had f of x is equal to x cubed plus 1/4 x, and we had to show that f of x is strictly increasing over its maximal domain. So now the question is asking us to find the x intersection or intersections between f of x and f inverse of x. So what most students would do is they would say, okay, I need to solve for f of x is equal to f inverse of x, and then equate those two functions together to therefore find the x intersections. But what happens when you actually try to find the rule of our inverse function of f of x? What actually happens is that this is what you would usually do, right? You would inverse and you'd say, okay, swap x and y. So this is a statement just to specify that I'm finding my inverse function. So if I try to do that for this equation, what happens is I get x is equal to y cubed plus 1/4 y. Now it's kind of interesting that we have two instances for y that we actually can't combine in this case because they're not like terms, and therefore we actually can't rearrange for y to find the equation. So how can I find, if I can't find the inverse function, how do I actually find the intersections between the function and its inverse? So this is where a really important concept comes in VCE methods, and I've seen it so many times in SACs and exams as well. It's where the intersections of f of x and f inverse of x usually lie along the line y is equal to x. Now I say usually because 99.9% of the time it does, but sometimes it actually does lie in the line y is equal to negative x, but that's kind of a story for a different video. What we're going to do is focus on the majority case, and that's where a function and its inverse lie along the line, or the intersections lie along the line y is equal to x. And the best way of confirming that is just purely through a graph. So this is roughly what the graph of f of x looks like. So if I imagine the inverse function, it's just going to be a reflection in the line y is equal to x, which looks something like that. So the shape is going to look something like this as well. So I can see roughly from this graph that the intersections between the f of x and f inverse of x do lie along the line y is equal to x. I'm unsure of if there's one intersection or three intersections. The way that there could be one intersection is if the graphs look something like this. So it could be something like this where the graph's a bit more extreme, like that, and it actually doesn't have the chance to intersect after x equals 0, something like that. But in this case, or in this graph, I've shown it that it does have three intersections. I'm unsure of which case is which in this case. So what I need to do is just evaluate f of x is equal to x, because intersections do lie along the line y is equal to x, again, for 99.9% of cases. And this actually allows us to find the intersections between a graph and its inverse function without actually knowing the rule for the inverse function. And this is a very common question. Again, I've seen in a lot of SACs and exams where a lot of students fail to recognize this. And from an easy question that should be guaranteed marks, they're not even doing an attempt because they can't even find the inverse function. So just keep in mind, whenever you have a function and its inverse, the intersections 99.9% of the time lie along the line y is equal to x. So this actually becomes a very easy problem where I'm literally just solving x cubed plus 1/4 x is equal to x like that, and just rearranging for x and evaluating it. So what I could do is move the x to the other side. So I get x cubed minus 3/4 x is equal to 0. And I could factor out an x. I get x outside of x squared minus 3/4 is equal to 0. Therefore, I just do the difference of two squares with this bracket here. So I get x outside of x minus square root of 3 on 2 outside of x plus square root of 3 on 2 is equal to 0. So therefore, I can see that there are three solutions to this equation, which therefore means that there's three intersections between f of x and f inverse of x. So therefore, I say x is equal to 0, square root of 3 on 2, or negative square root of 3 on 2 as my final answer. Done.